Okay, let's get going here. Okay, now let's say we have a function f of x. We're going to be talking about the maximum value of f of x. Now, there are practical applications of maximum and minimum values of a lot of things that we're going to be doing in this chapter, but a lot of it is also pure mathematical theory. And you really need to understand this theory in order to understand the practical applications. But more importantly, the AP exam has math theory in it. And the AP exam is an expertly designed exam to flush out students' misconceptions. So we don't want any of you to be flushed out. So let's really make sure we understand this stuff. Okay, so check out page 279 in your textbook. The first thing we want to look at is the definition of an absolute maximum. A function f has an absolute maximum or global maximum at c. If f of c is greater than or equal to f of x for all x in the domain of f. And the number f of c is called the maximum value of f. All right, so here's our function f. Now, there's some c value where f of c is greater than any other f of x value. Now remember, f of x values are up and down. So f of c is higher than any other f of x value. That makes f of c the maximum, the absolute maximum. Now, c is the location of the absolute maximum. And that's an important distinction. A lot of students fail because they say that c is the absolute max. It is not. The absolute max is the highest point on the curve, and when we're talking high and low, we're talking f of x, not x. So f of c is the absolute maximum, c is the location of the absolute maximum. Now, likewise, if we have a function g of x, then we have a point d, g of d, that's the absolute min of the function, because g of d is less than any other g of x value in the function, g. And d is the location of our absolute min. Okay, so that's important to understand, that the location is your x value, the actual min or max is your y value. Okay, cruising on. Okay, so we talked about the absolute max and the absolute min. Next, we're going to talk about the local max and the local min, or what I prefer to call it, the relative max and the relative min. So over on page 280, we see function f has a relative max at c if f of c is greater than or equal to f of x when x is near c. Okay. Right here I'm showing you the difference between relative and absolute. F of a is the absolute minimum of this function here because there is no other point in f that's less than f of a. So f of a is the absolute minimum. Now, f of c is a relative minimum. It's not the absolute min because a, or I should say f of a, is below f of c. But f of c is a relative minimum, and c is the location of that relative minimum. Now, when we talk about the maximums, notice this function goes up to the left and up to the right. So there is no absolute maximum, but f of b is a relative maximum. And b is the location of the relative max. Now, notice what it's saying on the definition. F of c is greater than or equal to f of x when x is near c. Or in our case, f of b is greater than or equal to f of x when x is near b. Well, what that's saying is that f of b is the highest point in the neighborhood. What neighborhood? Well, that could change depending on what you're referring to, or it could change depending on the function. But I could say that I am the best table tennis player at Brethren Christian. That would be true. I'm the best table tennis player at Brethren Christian. Now, if you go outside of Brethren Christian, I'm clearly not the best table tennis player in the world. Well, at least not anymore. But, so, that's the difference between a relative max and an absolute max. Whoever's number one in the world would be the absolute max. And I'm the max in this little neighborhood. Okay, so relative min. I'm sorry, absolute min, relative min. Now, f of a is also a relative min, but it's also an absolute min. Now, f of b is a relative max. There is no absolute max. Okay, so cruising on. Now, the extreme value theorem. This states that if f is continuous on some closed interval a, b, which means f is continuous from a to b, including a and including b. And remember, a and b are x values. Okay, so f is continuous from one point to another, then f obtains an absolute max, f of c, at some x value, c. And it obtains an absolute min, f of d, at some x value, d. Now, this is a theorem that has been proven and is absolute fact. So, didn't we just have an example where we had no absolute max? But this is saying if f is continuous on a to b, that f obtains an absolute max at some x equals c. How does that work? Wrong way. Notice we said there is no absolute max here. Well, the extreme value theorem is saying you have to put limits on your function. So in other words, we have some point A and some point B that it's between. Let's just do it over here. Come on. Okay, so if I have a function, let's say my function goes like this. And notice I don't see any maximum value here. Well, the maximum value is the beginning point A. So f of A is the absolute max. And f of B is the absolute min. because our function doesn't go forever to the left, forever to the right. It goes from A to B. It includes A, f of A, and B, f of B. So that means f of A is the absolute max, f of B is the absolute min. Okay, now take a look on page 281, and you can see what some variations of what we're talking about. Figure 5, notice you've got points A, B, C, and D. Now, A and B are the endpoints, but C is the location of the absolute max here. Now, if you look at the second diagram in figure 5, then A and B are still the endpoints, and C is still the location of the absolute max. Now, notice in the second diagram, the location of the absolute min is the right endpoint, because it's lower than any other point in the interval. And then in the third diagram, you've got two absolute maxes, C sub 1, C sub 2. You've got one absolute min, and that's at D. And now, in figure 6, notice there is no absolute max there. So, does figure 6 contradict the extreme value theorem? No, it doesn't, because it doesn't have the hypothesis. F has to be continuous on A to B. Well, in figure 6, the function is not continuous from A to B, so there is no max there. Oh, and incidentally, if you think the max is that open point there at x equals 1, that's not an absolute max, because the function is not defined there. So then you say, well, it's infinitesimally close to that. Well, then what's the value of the absolute max? Is it 1.9? No, it's bigger than that. It's 1.99? No, it's bigger than that. 1.999? No, it's bigger than that. 1.99999 for forever? No, because if you have 1.999 forever, that's equal to 2, and 2 is not defined there. So figure 6 has no maximum value, no absolute maximum. Now, figure 7, same thing. There is no absolute min because it's not defined at x equals 0, and there is no absolute max because it approaches infinity, so it's not continuous from A to B. So once again, that does not contradict the extreme value, the extreme value theorem. Remember though that that is a requirement of the extreme value theorem, that a function has to be continuous on a closed interval, which means including A and including B. And if that is true, then that function will have an absolute max and an absolute min. Okay, cruising onward. Now, this guy's name is Fermat. You don't pronounce it Fermat, that makes you sound like a complete doofus. So, Fermat, Fermat's theorem. Now, Fermat says that if f has a relative max or a relative min at some x value, we'll call it c, and if f prime of c exists, then f prime of c must equal 0. Okay, so if I have a relative max at some c value, then, and notice it's continuous and f prime of c exists, then f prime of c must equal 0. the slope of the tangent at the maximum has to be 0. And likewise, if I have a relative min, where, and we'll call this C also, a relative min, the slope of the tangent is also 0. So that means f prime equals 0. So the requirements are there has to be either a relative max or a relative min at some x value, and the derivative must exist at that x value. And if those two things are true, then you're guaranteed that the slope of the tangent, f prime of c, will equal 0. Okay. Now, next, we're going to talk about critical numbers. A critical number, let's put it like this, a function f has a critical number at some x value if and only if f prime of c equals 0 or f prime of c does not exist. That's what a critical number is. It's an x value, or I'm sorry, the critical number is actually the y value. The location of the critical number is the x value. But the critical number is going to be the place on the function where either the derivative is 0 or the derivative does not exist. The critical number is the x value of a relative min or a relative max, or a point where the slope is infinity. So now, the next thing, we've defined a critical number. That could be a min, could be a max, or it could be a place where the function's undefined. Now, how do we find the absolute max of a function on some closed interval from a to b? First thing, we find all the critical numbers. How do we do that? Well, we take the derivative of the function, set it equal to 0, and solve for x. So now we have all the x values where the derivative equals 0. Then, we compare those f of x values with f of a and f of b. Those are the endpoints. So the greatest such f of x value is the absolute max. And the x value of that point is the location of the absolute max. The least of those f of x values is the absolute min, and the x value of that absolute min would be the location of the absolute min. Now, sometimes your absolute max will be the relative max. Sometimes the relative max will not be the absolute max, but the endpoint will be higher than the relative max. So you have to compare the endpoints with the relative maxes to find the absolute max, and you have to compare the endpoints with the relative mins to find the absolute min. And that sounds all nice and easy, but it's so simple to forget about the endpoints. Find that relative min and go, oh, that's the min, that's it, game over. And then the AP exam says, no, it's not it, you're wrong. It's the endpoint. So always remember to check endpoints anytime you're trying to find an absolute max or an absolute min. Now, I want to give you a little preview of coming attractions. An absolute max, or a relative max, this is going to be the point where the derivative equals 0. Now, how do we know if the derivative is 0, if that's a max or a min? If I go slightly to the left of that and the derivative is positive, then I go slightly to the right of that and the derivative is negative, then that says for sure I have an absolute max. Now I could go a little bit left and see if the y value is greater or less, and then go slightly to the right and see if the y value is greater or less. But really it's simpler to see if the derivative goes from positive to negative, then you would have an absolute max. Now if the derivative goes from negative to positive, then you have an absolute min where f prime equals 0. Okay, so that's basically the end of the theory to this chapter, or this section. So let's check out some example problems and make sure we know what we're doing. So all right, example 1. f of x equals cosine x takes on its max values of 1 infinitely many times. Likewise, cosine 2n plus 1 pi equals negative 1 is its minimum value, where n is any integer. Okay, so basically what that's saying is an absolute max or an absolute min is a y value, not an x value. Okay, let's check that out. All right, here's y equals cosine x. Now I would say, what's the absolute max? And you might go, oh, well, there's a bunch of points that are tied for the absolute max. Well, no. The absolute max is y equals 1. That's the absolute max. Now, if I say, what's the location of the absolute max, then that would be 2n pi. 2n pi is the location of the absolute max. But the absolute max is y equals 1. Remember, absolute max is the y value. Now, the absolute min. These are not relative mins, once again. These are absolute mins, or I should say this is an absolute min, and that is negative 1 is the absolute min. Now, where does the absolute min exist? That exists at y equals 2n minus 1 times pi, or any odd pi value. So negative pi, 1 pi, 2, negative pi, 1 pi, 3 pi, 5 pi, 7 pi, so on. Those are the locations. The absolute min is negative 1. The absolute max is positive 1. Okay. Example 2. f of x equals x squared. Now, there is an absolute min there at x equals 0. What is the absolute min? It is 0. So the location is x equals 0. The absolute min is y equals 0. And there is no absolute max because it goes up forever both sides. Okay. Take a look at example 4. Oh no, we'll look at example 3. Okay, f of x equals x cubed. Now notice this function has no absolute max, no absolute min, because the only place that f prime equals 0 is at x equals 0. And that's not an absolute max or an absolute min. That's called a point of inflection. Okay. Example 4, we've got this function f of x equals 3x to the fourth minus 16x cubed plus 18x squared. And notice then, if I want to say that the interval is from negative 1 to positive 4. Now, the relative max is located at x equals 1. And the relative max would be 5. But that's not the absolute max, because the absolute max is when I put in negative 1 into the function, I get 37. Well, that's a lot bigger than 5. Or if I put in 4 into the function, what is f of 4? They don't tell us. That's obnoxious. Let's see. F of 4... Yeah, that's just not worth plugging a 4 in. That's just going to be too much of a mess. Yeah, my calculator is actually at my desk too, so forget that. So, clearly from the graph, 37 is the absolute max, and it's located at x equals negative 1. 5 is a relative max located at x equals 1. And negative 27 then is the absolute min located at x equals 3. Now when we're talking about the minimums, 3 is the location of the relative min. That's where f prime of x would equal 0. Let's just do this real quick here. Oh, I know what we should do. Okay. 3x to the fourth minus 16x cubed plus 18x squared. Oops. All right, so there we are. Now we're going from 1 to 4. So at, we're going to need to zoom in here a little bit. All right, so x equals 1 still goes, oh no, I guess we need to zoom out a little bit. Yeah, we need to keep zooming. Okay, so there's our function now. And we can see that at x equals 1, we're going to have 37. And x equals 4, we're going to have, let's see, 10, 15, 20. Yeah, so at x equals 4, it won't quite be that high. Now, let's look for our absolute max and our absolute min. So what we're going to do is we're going to say if y equals 3x to the fourth minus 16x cubed plus 18x squared, then we go y prime equals 12x cubed minus 48x squared plus 36x. And we're going to factor out a 12x out of here. So 12x times the quantity x squared minus 4x plus 3. So this is 12x times x minus 3 times x minus 1. So, where is okay, so where does f prime of x equal 0? At f prime of x equals 0 at x equals 0, x equal 1, x equal 3. So x equals 0, x equals 1, and x equals 3 are the critical points. Those are the locations where f prime of x equals 0. Now, if we want to know if we have a relative min or a relative max, the derivative at x equals -1. If I go to the left of 0 at all, if I go to the left of 0, then I have negative times negative times negative is negative. So the slope here is negative. Now, if I go to the right of 0, I have positive times negative times negative, and that's positive. So I'm going from negative to positive at x equals 0. That makes that a relative min. Now, is it the absolute min? Well, you have to compare that with all the other critical points and then compare it to the endpoints. Now, if we check out x equals 1, then that's going to give me a derivative of 0. Now, let's check out x equals a half. If I put 1/2 in here, I have positive times negative, which is positive. So at x equals a half, I have a positive slope. At x equals 1.5, or no, 1.5, x equals, let's say, yeah, right, I want to go just slightly to the right of 1. So if it's 1.5, then that would be positive, negative, positive. That's negative, so it's going from positive to negative slope. That's a relative max. Now, is it an absolute max? Of course not. You can see that it goes way higher. Now, the third point, x equals 3, I go slightly short of 3, and I'm going to go positive, negative, positive. That makes a negative slope slightly to the left of 3. And then slightly to the right of 3, it's going to be positive, 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 and that gives me a positive slope. I went from negative slope to positive slope, means relative min in between them. Now, if I plug in x equals 3 into my original function, my y value will be least of any other y value that I could ever plug in. So that makes x equals 3 the location of the absolute min, and x equal 1 then, I'm sorry, x equal -1 would be the location of the absolute max, because the relative max doesn't compare with the endpoint maxes. So that's basically what we're doing in this chapter. Now, take a look at example 6. The function f of x equals absolute value of x. Now, we want to know where the absolute min is. Well, let's put this on the graph, too. Okay, here's our function, and we want to know the absolute min here. Well, notice, just looking at it, you can see the absolute min is 0. Now, how can I prove that? Well, where are the critical points here? Well, the critical points are where f prime of x equals 0 or does not exist. Now, there is no place on here where f prime of x equals 0. At x equals 0, f prime of x does not exist. Because remember, the derivative does not exist where there's a corner or a cusp. So there is no place on here where the derivative exists. But at x equals 0, we have a critical point. Now, what we do is we examine the critical point relative to any other point on this function, and the y value will be less than any other point on this function, making x equals 0 the absolute min. Now, if I make this a an interval from, say, negative 20 to 20, well, then the absolute max will be the endpoint. Whatever the endpoint is will be my absolute max, because there is no relative max here, so the endpoint is the absolute max. So this is the kind of thing that we need to understand for this lesson, is finding the derivative, setting it equal to 0, finding the critical points, and then evaluating the critical points as absolute or relative mins or maxes, or just places where the function's undefined. So that's it. Have fun with these.